right, hi everyone. So I want to start by making a quick announcement. There was some students were asking me today about there's an invitation for a conference set up. So one of the students had requested, since the student wasn't able to make it today, requested that if I could just turn the conference on and she could log in remotely. So she's doing that, and that's why many of you all may have received those notifications as well. So it goes to saying in the future, we're trying this today. I think hopefully it'll work fine. If any of you have an extenuating circumstance where you would like to be able to log in remotely, you're out of town for a professional meeting or something like that, or for whatever reason, just let me know. I'll get the remote conference started up so that you can see it live. Let me just make sure that Falak, if you're there, please send me a message. Please send a message, say that you can see the screen. Okay, great. Okay, so today, as I said, thank you. I see most of you have brought your laptops today. What I'd like to do today is we're going to spend a portion of the class talking about orthogonal coordinate systems, the Cartesian, cylindrical, and spherical system. And then we're also going to spend a good chunk of the class today talking about how to do plotting in Python. And so you'll notice that on Canvas, on Canvas here, there is a link. If you go under modules, I changed the module a little bit. I took out a bunch of links and I added a link to just a GitHub site. If you click on this link, sample Jupyter Notebooks, you click on that, you'll get to a GitHub site where there are all the sample notebooks that we're going to be going over in class today. Actually, we might not be able to get to all of them, but we'll be able to get to hopefully some of them today. So that's the plan, and I've already downloaded those notebooks. So they are, hold on, let me close this. I have too many windows open here. All right. So I have my notebooks loaded here. So starting off, did everyone get a chance to, has everyone turned in the assignment, which was basically like loading up IPython or Jupyter Notebook on your laptops, printing out your name? Let's show of hands.
I use MATLAB. Is it okay?
Yeah, since for this particular assignment, MATLAB's okay because I changed the assignment kind of late. But in the future, have you had a chance to load up Jupyter Notebook on your laptop?
Yeah.
Okay, then you're fine. You're fine. Yeah, because like I said, over the weekend I decided, let's just focus on Jupyter and Python this semester because you've all had experience with MATLAB before. I want you all to have this experience in knowing how to plot stuff in Python and just getting comfortable with it because it's a very powerful programming language, and I think that it's eventually going to overtake MATLAB. And for those of you going into data analysis, Jupyter and Python is really the way to go. Okay, so let us quickly talk about, what did we talk about last time? In this module, we started by talking about basic vectors, what vectors are, addition and subtraction. We talked about two ways that you can multiply vectors using the dot and cross product, and I showed you some examples how to do that in Jupyter and in MATLAB. Last time in class, we talked about gradient, divergence, and curl. And we also talked about the how to do partial differentiation. We still haven't talked about doing integration. Then eventually we're going to talk about how doing line integrals and surface integrals. Okay, so that's going to be the next class. So let me just fast forward here. We saw some examples of vector multiplication, cross product, and so on, and what the physical meanings are. And now we are. We talked about the gradient last time. And then we finished by talking about partial derivatives. We finished talking about divergence and curl also. I forgot to mention that. All right, so we have an idea of what those are. All right, so it's important that you're able to visualize fields in 2 dimensions and 3 dimensions. You can plot vector fields by hand, but every single point in a 3-dimensional space, if you imagine having to draw a vector, it's quickly going to get tedious. So we use softwares to do that. The types of plots that we're going to be going over today, we're going to start with simple line plots and simple vector plots. Then we'll get to doing 2-dimensional surfaces and 3-dimensional surfaces. And then we'll get to 2-dimensional and 3-dimensional vector plots. Okay, as I said before, you could do this in MATLAB as well, but I think this semester is good for us to all learn a little bit about Matplotlib and Python. The comparison between the two, we went over it in the end of class last time, just really quickly. Python is a free and open source programming language that's become probably one of the most popular programming languages today. It's used widely in data science. It's used widely in a variety of engineering companies. It's connected to the Python programming language, which is a very, very powerful programming language that's also relatively easy to read, easy to use. There are aspects of Python and aspects of Matplotlib which is very similar to MATLAB. In fact, a lot of it's modeled after MATLAB. MATLAB is a software for numerical computation. That's matrix math, linear algebra that's been around for a couple decades now. It's a paid software. It's a very good software, and it's widely used in a lot of engineering companies. And I think a few of you use MATLAB already in some of the work that you do at your companies. So there are a bunch of tutorials for MATLAB that you probably have seen in your other classes. I've also enclosed some tutorials for Python. These are 2 very common tutorials that are relatively quick that you can do if you want to get familiar with the Python programming language. And this third one is a list of 10 free online courses that you can do to take Python for beginners. Specifically to Matplotlib, this is a package within Python that's used to make 2-dimensional and 3-dimensional plots. Quite powerful. These are the tutorials, and if we click here, there's you can see that there's a tutorial on how to go through it step by step, and there's also a gallery. If you're curious about the types of plots you can do in Matplotlib, this is a gallery. You can see that there's lines, bars, and markers, plots. There are line plots, as you can see here. Categorical variables is a combination of bars and scatter plots. You can do different colors. You can do error bars. Let's make this a little bit larger. Error bars, where you add like a vertical or horizontal bar to indicate what kind of level of error you have. These are types of scatter plots and line plots. You can do interesting stuff like polygon plots, histograms, which is used a lot in data science. What else here? There's a lot of ways that you can customize it. And there are some interesting ones that you can do, like a scatter plot with different sizes of dots to represent a third dimension of data. You can, a lot of times, I don't know if any of you read like New York Times or other like newspapers where they do a lot of like data visualization. They use libraries like this to do a lot of this stuff. It's pretty neat. A lot of these fancy types of plots are used in data science right now. You've probably heard that term. It's I would say one of the most sought after careers at this point in time, because the data science has just become like very popular. It applies to a lot of different fields, and the salaries tend to be really good. By the way, this is something interesting. This is something the department chair forwarded to all of us yesterday. It turns out that if you look at the median salaries of people graduating from the undergrad degrees and the level of debt that students have, if you look at those 2 factors, apparently like Wayne State, University of Michigan Dearborn, University of Michigan Ann Arbor, Michigan State, they're all within the top 10 schools in the country. It's kind of surprising. I was like, why is that? That's really interesting. But apparently in the Detroit area, a lot of our undergrads, they complete their degree and they already have a relatively well-paying job when they get out. So because of that reason, like the Wayne State is number 8, U of M Dearborn is in a similar range, U of M Ann Arbor is like number 9, and Michigan State, I think it's also in there somewhere. That these are all like, apparently in Michigan you have some of the highest starting salaries for people coming out of electrical engineering programs. So related to the median salaries, our Michigan universities, including Wayne State, are all in the top 10. I thought that was pretty interesting. Okay, anyway, continuing, like there are different timeline graphs, correlation graphs. There's two-dimensional plots, which we're going to talk about today. A lot of fancy stuff that you can do, okay? So you can look through this and see, whatever plots you're kind of interested in. If you all read scientific papers, you know that they love to put like very beautiful and fancy plots on there. Okay, so I won't belabor that any longer. We'll just get right to it. So most of you have installed Anaconda. You did a show of hands. It's an easy way to install and run Python code on your system using a web browser. So if you follow the instructions for installing Jupyter Notebook, you should see something like this. All right, I created a link below here from Anaconda. There's a link to start the Jupyter Notebook. Let me just start up Anaconda so that we are all on the same page. So if you have installed Anaconda, just go ahead and start that up. I just want to briefly talk about what's in Anaconda, and then we'll get to Jupyter Notebook in a second.
So is the code similar to MATLAB?
It's very similar to MATLAB, yeah. You'll see some of them, I would say like it's like 60% similar, 40% different.
Okay. Is it a loop is same thing too?
I'm sorry?
The loop?
Is it a loop?
No, loop function?
Is it a loop function?
Yes.
The question is, can you do loop functions in Jupyter Notebook and Python?
Yeah.
Oh yeah, you can definitely do loops. The format might be slightly different, but we're not going to be actually doing any loops today. We're just going to be using some plotting functions. And you'll see that the plotting functions can be similar with MATLAB. All right, so let's see. Where's my Anaconda window? Okay, there we go. After you install Anaconda, you'll see something like this. Okay. Now there's a bunch of shortcuts that you have here, because Anaconda, what it is, it's installing the Python programming language on your system, and it's also installing a bunch of other things, a bunch of different tools. Jupyter Notebook is a tool that we're going to use today. It is a tool where you can actually do Python computation, kind of like having a MATLAB window, except it's in your web browser, which is pretty neat. Because what's often used is if you're doing like data science, a lot of data science needs to be done on like high performance servers, servers with like 120 cores in it. Okay, so that's Jupyter Notebook could be running on that high performance server, and you could just log in remotely and do a lot of your computations that way. So it's purely web based, as you'll see after when you start up Jupyter Notebook, you'll see something like this. And so what's happening is, when you start Jupyter Notebook, you'll probably see a window like this. And what Anaconda is doing, it's starting up a process on your computer, and that process is creating a web server on your computer, and that web server has the Python kernel built into it, so it can run any Python command that you want. So it starts Python on your system, and at the same time, it also starts a web browser. And after you start up, you'll see that the last thing it usually shows, it'll show you, it'll have the link. So you can click on the link to start up your web browser, and most of the time it'll just start up a web browser on its own, and it'll go to the URL. So the URL, notice that it's called localhost 8888. That what the localhost means, go to the web server. If you put like Amazon.com, you're going to go out to Amazon.com's IP address, and Amazon.com will reply to you. Localhost means you're going to go to the web server that's running on your laptop, and that web server is going to return to you information. Okay, so this it's a special URL. The 8888 means it's a port number. Web servers run on different port numbers, and it so happens that you can configure Jupyter to run on any port number you wish, but the default one is 8888. So once you get to that, you will be able to browse through your computer. For example, like I'm in this directory right now. I have a directory on my computer that has all the stuff with our class, and I just clicked on this, and I have all the IPython notebooks downloaded to this directory. So I suggest that you download the IPython notebooks from Git. Has everyone been able to download those? Not yet. Okay, so click on the link, go to Canvas, and you click on the link with sample Jupyter Notebooks. And that'll bring you to this page. All right. And what you can do here is you can just go to clone or download. And you can just download the zip file. Then extract it, and you'll be able to see all the notebooks there. Okay. So then you can open these in Jupyter Notebook. All right, so while I'm talking, everyone please go ahead and get those started. And then I will go back to my Jupyter Notebook and I'll start talking. Okay, so I had these from last semester, so I just want to make you all aware that MATLAB also has two-dimensional and three-dimensional graphing functions. We went over some of them in Python, and here's the similar functions that you've probably used before in MATLAB. All right, so there's two-dimensional and three-dimensional plotting functions. And MATLAB also has these functions, gradient, divergence, and curl built in. I'm going to show you how to calculate them separately in Python. And there's also functions called mesh grid and linspace. Has anyone used linspace before in MATLAB? Okay, what does linspace do? It's a limit. Yeah, it has limits in it.
It creates like an array. You can set like two numbers, but then you can set how many.
Exactly.
Like
Yep.
say like
That's right. That's right. You're both correct. So linspace is a function that allows you to create a vector of equally spaced points. So let's say I did linspace going from 0 to 10. All right, those are my two limits. And I want to pick 10 points from 0 to 10. So it'll be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's 11 points. But you got the idea. It'll give you 11 equally spaced points between the limits that you specify. This is very useful for graphing things. And we'll get into mesh grid. If you want to do two-dimensional and three-dimensional plots, then you have to use linspace and mesh grid. So it turns out both of these functions are available in Python as well. MATLAB has some nice functions to be able to convert between Cartesian and polar coordinates and spherical. I'm going to show you how to do those in Python just using the underlying functions. All right, so let me just skip over these. If you're interested, you can go over them yourself with how to do the vector plots in MATLAB. Two-dimensional and three-dimensional vector fields. You can do these using a set of simple functions here. And you'll see that we can do the same thing in Python as well. Plotting scalar fields and gradients. This is another thing you can do in either software. So a vector field, as you know, is every point in a two-dimensional space, there's going to be a vector. And a vector is simply an arrow pointing in a certain direction, and it has a certain length associated with it. So it has length and magnitude. In a vector field, you have vectors defined in a two-dimensional space, or you have vectors defined in a three-dimensional space. Okay, now obviously you can quickly see that drawing these by hand would be pretty awful. All right, so these are the formulas. We've gone over what the definition of vector fields are. We also talked about scalar functions and scalar fields. So the difference between a vector and a scalar is that a vector is an arrow defined at every point. A scalar is not a vector. It's just a scalar quantity defined at every point. So if we want to take a simple example of a scalar function, here's one where it's a function of x and y. So this is, you can think about this as z is equal to f of xy, and that's equal to x squared plus y squared in this example. And you can see a plot of that function here. It looks like a surface. At every point xy, there's a corresponding z. Okay, and this is the way that you would plot that kind of surface in MATLAB. We talked about gradients last time, and I just want to hammer in another example of a gradient. What's being plotted at the bottom here, you see these arrows here. the blue arrows, that is the gradient field. Okay, just remind everyone, the gradient, it operates on a scalar function. Okay, the gradient operates on a scalar function and it gives a vector as a result. And the way that we physically think about the intuition behind what the gradient is, in the example of an f of xy function, you think about this function as like like if you were going hiking, like we said last time, like you're walking on the surface and the surface has some kind of slope on it, like the mountains are up here and the valleys down here. So the gradient points in the direction that you should walk if you want to get the maximum increase in slope. And so you can see these gradient vectors down here at every point x, y, there's an arrow defined. And that arrow tells you what, if you are at that point x, y, what direction should you go to get the maximum increase in slope, to go most uphill. All right, so that's why you see that at the bottom of the valley, the gradient vector is 0, because the slope at the bottom of the valley is 0, right? So there's no direction that you can go regardless of whichever direction you go, the slope is going to be in the same direction. Versus if you're somewhere over here, for example, there's a clear direction in which way you should go to go uphill. Right? So that's how I like to think about the gradient. The mathematical definition of the gradient is the direction points in the direction of maximum slope, and the magnitude gives you the slope in that particular direction. All right, so let's get to, we're going to do plotting lines and surfaces and vector fields in Python. So there's 3 things we're going to cover. So let's talk about lines first. And I have the information here in the slides just for your reference purposes, but what we're really going to do is the same information is also in the actual Jupyter Notebooks. So we're just going to go ahead and look at that. Before we start on that, any questions so far? Okay, has anyone had any issues like getting Anaconda and Jupyter Notebook installed? Are you able to access it through your web browser? Show of hands? All right. Okay, some of you don't have your laptops here, but then you'll have to like go over it afterwards in class, or afterwards. Okay. So let us go to let's do the first one. Let's do line plots. So just a little bit about Jupyter Notebook. There's an interface here. You can open, if you click on one of these, it'll open in a separate window. All right. There are other things you can do here. Is you can click New. If you want to create a new notebook, you can go to New, Python 3 notebook, and then it'll open up a blank one for you. Here you can see what notebooks are running. So every notebook that you run is a separate Python kernel, and you can shut them down, you can restart them. The cluster thing you don't have to worry about. You can order them by file size and name and stuff. That's all, I think, pretty intuitive stuff. Okay, let's look at the window now. Let's see, maybe I can make this a little bit bigger. That might help a little bit.
Professor?
Yes.
Just a quick question.
Yep.
How do we know which libraries are going to be needed for which single purpose? Are you going to tell us before, or is there a way to just look into libraries and see what does I know in C++ they gave us a list.
Yep.
And showed us this would get math directory and something like that.
Right.
So
right.
Is there a list somewhere else online?
Yes. So the question was, how do we know? This is actually related to the first part here. The first thing we do in our notebook is import the required libraries. So the question was, how do we know what libraries to import? Is there a list of libraries somewhere? Yes. So you can go here and do the Python standard libraries. So first of all, just to remind everyone, a library is a package of code that you can use in your software that you create. C++ has a lot of different libraries for doing I/O, different math type things. Python has a massive set of different libraries. Some libraries are part of what's called the standard library. So these are built-in functions and built-in constants. all of these libraries are you get them basically for free when you install Python on your system. When you install Anaconda, you get not just the libraries that come with Python, but you also get a whole bunch of other libraries that are very commonly used in scientific computation. This is the reason why actually Anaconda exists. If you were just using Python on its own, you could just download and install Python. But what Anaconda does, it tries to give you not just Python, but let's say all the popular libraries. Let's say Google has their TensorFlow library. There's an organization that maintains this library called NumPy, which is for numeric computation, very MATLAB-like. There's an organization that maintains a library called scikit-learn, which is all the machine learning libraries. There's organizations that that maintain libraries for doing various types of plotting or image processing. So there's tons of different stuff. And what's nice about Python is that there are all these libraries available for free. Okay, with C++, sometimes you run into this issue is that you have to buy a library from a company, and that company will charge you money for it. With Python, the culture seems to be that all these libraries are just available for free, which is why I love it quite a bit. So if you look in your, if you look where it says environments, you will see something like this, where it says the base or root environment. And you can create different environments that have different sets of libraries. We're not going to be doing that right now, but you can just look under here and see that these are all the different libraries that happen to be installed. We are just going to be using like 2 or 3 of these libraries today, okay? But Anaconda comes with a whole bunch of these different ones that are commonly used in scientific computation. All right. Anaconda also has a way for you to install additional libraries. So for example, I can click here and go to not installed so I can see what's available. And if I click on one of these, I can go ahead and install it down here. You can't see the apply window very well, but that's how you manage the different libraries on your system. So in order for you to be able to close this. The first thing that we're going to see in our Python notebook is these import statements. The import statements will only work if the library has already been installed on your machine. So you have to check. So if we look import numpy as np, I will go here. I can go to Anaconda, and I would want to actually confirm. I already know that Anaconda installed it, but just so you all can see, if I search through the packages that are installed on the system, you'll see that numpy, it's an array processing for numbers, strings, records, and objects. This is a very MATLAB-like interface for numeric computation. The second library we're going to be using is Matplotlib, which is a publication quality figures in Python. All right, so that gives you an idea, okay? All right, now let's get to the actual notebook. Does that answer your question? What was your name? Sorry, I missed it. Siva? Yeah. Does that answer your question?
Yes.
Okay, great. Once you get into the notebook, there are these things, they're called cells, okay? Cells are basically little segments of code or little segments of what's called markup. There are 2 different types of cells that I primarily use. You'll see that you can select the cell type here. You can either select a cell to be a markdown, or you can select it to be code. These other 2 I don't really use that frequently. All right, if it's markdown, the purpose of a markdown cell is for you to like document stuff. Let's say like me, you're trying to explain what your code is doing or what this notebook is all about. I'll just have a little segment here that explains what this is about. And there's a simple way that you can document this stuff. It's very similar to Wikipedia. You know, if any of you have edited stuff on Wikipedia, there's a certain format that you use. If you want to make a bulleted list, you put a star. If you want to make headings, you use the hashtag. And URLs show up on their own. So it's a simple like little markup language for doing that. So this is the more important one, I would say. Then you have certain cells that contain code, and this is the code that's going to be executed or run when you have your Python code that will be executed here. So let me see if I can put this in full screen. I think that'll be easier. View, let's see, full screen. There we go. All right, that's a little bit better. All right, now if you look at your window up here, before we get into the cells, I just want to walk you through what you can do here. So file, some straightforward stuff. You can you can open a notebook, you can save it as a different name, you can download it to your, separately, you can print it out and so on. You can close and halt it. Under edit, you can cut and paste different cells. I mentioned cells are different, just segments of code. For view, we're not going to just, we won't go over that yet. You can insert cells above and below. You can run certain cells and skip others. And then you can go to the kernel window. The kernel window is, let's say you run some code and for some reason the Python kernel, the thing that's running your Python code, let's say that it like locks up for whatever reason. Something's not working. You can actually restart the kernel here. So I'll just go ahead and show an example of that. So I'll restart it and clear all the output. All right, now all the graphs that I had are going to be gone. Things are going to run from the beginning again. All right, there's also some shortcuts here to do the same thing. This is to save. This is to cut and paste. This is to go up and down a cell. You can see that this notebook just has like 3 cells in it. You can also run the kernel. You can stop it, restart it, and so forth. All right, so I have put comments under each one of these Python statements so you can understand what's happening here. The first cell contains a bunch of code. Oh, I'm going to move this under here. Move this cell down. It contains code that will import certain libraries. And the 2 libraries we're going to be using here is Matplotlib and NumPy. This is MATLAB-like computation and then a plotting library. So the import statements look something like this. You're going to import NumPy as NP. So this portion here as NP, what that means is every time I have NP like I have here, it's sort of like an abbreviation. Every time I mention NP in my code, it's going to know that that's part of the NumPy library. So when I do np.linspace, a lot of you, we talked about the MATLAB function linspace. What this is going to do is it's going to access the function linspace that's part of the NumPy library. Okay, if you don't do np.linspace, it won't know what linspace is because that linspace is not part of the basic Python programming language. All right, so the next statement here is matplotlib.pyplot as PLT. So this is what's called a sublibrary. PyPlot is a library that's part of Matplotlib's library. And this is the part that's actually used for plotting. And so we're importing this as PLT. From Matplotlib import. This is just another way that you can import something. I could have also done this as import matplotlib.cm, but instead I did from matplotlib import cm. So it's importing the sublibrary called cm within Matplotlib. And this is a library that supports different color maps. If you want to do 3D plotting, you have to import MPL toolkits. This is part of Matplotlib. It's a special toolkit for that, for doing 3-dimensional plotting. And we are only importing a single function from there, instead of the whole library. You can import just a portion of it. And that way it'll save memory a little bit. This last introductory thing here is a directive that uses what's called the Matplotlib notebook type method to make our graphs. If you use the standard one, it'll still work. It'll still give you graphs, but you won't be able to rotate the 3-dimensional graphs. Okay, so if you took this statement out, the system will still work. But since we're making 3D graphs, we'd like to be able to rotate them and move them, then we keep this statement in here. It's a directive. Okay, questions so far? Yes?
So on the first line, this says import NumPy as NP. NP could be X.
Oh yeah, you could change it to whatever you want. You could put your name on there, you know. But that whatever name you choose, that has to be the descriptor that you use further on. Yeah. So as it turns out, like Python has a lot of conventions. Also, you don't have to use NP, but most people do. Like PyPlot, most people use PLT as the abbreviation for PyPlot. But like I said, you don't have to. All right, let's go. The first thing we're going to do is we're going to plot a line in 2-dimensional space. Now I'll show you the code to do that here. So if we want to plot something, we have to first create a linear space we're going to create 40 different points from x equals -1 to x equals +1. And so what I'm going to do is I'm actually going to print, I'll just do print x so you can see what these look like. Print y. And for the time being, I'm actually just going to comment these guys out. All right, and I have an error. Name NP is not defined. Okay, the reason I got this error is because I didn't import my NumPy library. I have to execute this code first. So if you want to execute one of the cells, the way that you can do it is just press Control Enter. So I'd like everyone to just try that. Click on the cell where you do import the libraries and just press Control Enter. And what you should see is, if you saw this here, we'll do this again, where it says in, it'll show a star there for temporarily. And that star means that your computer is busy working. And when it's completed, it'll just show a number here. And that number indicates how many times you've executed that particular cell. All right? So is everyone able to run that cell using just Control Enter? Yep. Everyone's got a number on there? Good. All right, now go down to the next cell. You can click on this one, and again press Control Enter to run this. All right. Now, if you didn't make the same changes that I made, you're going to actually see a graph up there. But what I did here is I changed this a little bit, just so you can see what's happening underneath the hood. So x equals linspace, and what this is saying, I want to create 40 points, 40 values of x between x equals -1 and x equals +1. All right, so 40 equally spaced points. So when I print x, this is what I'm going to see. It'll start at -1, and then it'll have 40 different values of x in order, equally spaced, all the way up to 1. All right. And then I printed the x, the values, so then you'll be able to see this is what the x values are. Now, what's happening in the next statement here is I'm saying y is equal to x to the power of 2. MATLAB uses a slightly different notation. MATLAB uses the caret notation. The caret notation is something that looks like this, you know, like that thing. That's how you do powers in MATLAB, but in Python, you use two multiplication symbols, 2 stars. That means x to the power of 2. And so what this statement does, it takes every single value of x that was in this array, all the values of x, and for each one, it takes the square of each one of those components. So the first element of y, what's the square of -1? 1, right? So that's how you get the 1 here. The square of -0.948 is 9.0 times 10 to the -1, and so forth, for all 40 of these values. So it does this calculation very quickly. So what was your name?
Sang.
Well,
Sang.
Sang? S-A-N-G.
Yes.
Okay. Sang asked a good question earlier in the class, saying, like, do you have to use loops to calculate? You know, you could calculate all this stuff in a loop. You could say, like, for all the values of x, for each one of those values, calculate the square of each one of those values. But NumPy has it has a shortcut that when you just do x is considered a vector or a matrix, and when you take the square of that matrix, it does an element-wise square for each of the elements in the matrix. So it's a shortcut. You don't have to write a loop to do that. And it turns out it operates a lot faster than writing a loop. Okay, we're not going to be doing any loops in Python today, but if there's, you can look online on how to write loops. It's very, very simple, and we may be using them in the future. But for right now, we're just using this NumPy thing. All right, so everyone's with me so far. So we have 2 vectors here, a vector of x values, and then down here, a vector of y values. Now, all we're going to do is, the first thing we're going to do is we're going to plot plot every value of x with every value of y. All right, so I'm going to take away these print statements here, so you don't need them. We don't need them anymore. And I'm going to uncomment these statements. All right, this first statement here is going to create a new figure. It'll create a figure that we can plot our stuff in. The next statement here, plt.plot xy. So what it's going to do is going to take this vector x and this vector y, and it's going to take them as a series of xy points, and it'll plot like -1, 1, and -0.948, 9 times 10 to the -1. It'll plot each one of these as a series of xy points. The last two statements here, you don't have to do them, but if you want to label your x and y axes, you can do that. All right, so I'm going to press Control Enter. If everyone else has had a chance to do that so far, you're going to see something like this. All right, and here is your xy function. We're just plotting y equals x squared. All right, so all right. All right, this figure is quite large. So one thing you can do is you can control the figure size with just a keyword value here. You can do 2, make it a little bit smaller, easier to see. And once you're here, you can, it'll give you these x and y values that you're at. You can save this as an image. You can, zoom. You can zoom in and out. Although I can't do that with my touchpad, but you should be able to do that with the mouse wheel. Okay. Any questions so far? Yeah, back there.
What did Control Enter do again?
Control Enter just runs the cell. I want to run all this code, so I just press, I put the mouse in this cell, and then I press Control Enter to run it.
So Shift Enter is different?
Shift Enter will work also. Shift Enter will run the cell, and it'll take you to the subsequent cell. Yeah. So if I do Shift Enter here, you see how my cursor now went into the next cell, but it still executed the same part. So we can make this one a little bit larger here, and so you can see the x, y, and values here. All right, we had a question up here.
Yeah, where does the text 0.5y come from?
The text is coming from the position of where your mouse is.
No, like the output 9 at the bottom left of the screen.
That is just the output from this last statement here.
Oh, okay.
You can actually suppress, in MATLAB how you can suppress output by putting a semicolon at the end? We can do that.
Okay.
And you'll see if I run this now that text will go away. All right, so now let's do a line in three-dimensional space. Make this full screen so you all can see. All right. So what we're going to be doing now is we're going to draw an example of a helix. So a helix is a function that's defined in terms of a parameter theta. All right. There's an x, y, and z variable. Okay, so a line consists of a series of x and y points. That's the example that we just did here. A series of x and y points. A three-dimensional line consists of a series of x, y, and z points. Okay, and if you remember from maybe your math or calculus classes, another way that we can define functions is we can actually have different functions for the x, y, and z portions of it. And they can all be defined in terms of a parameter. So in this case, what's being done is we have this parameter called theta. All right, and that theta is we're going to be plotting it from theta equals negative 4 pi to theta equals 4 pi, and we have a constant value r and a constant value c. This is, if you look up on if you look up what is the formula for a helix, this is what you'll see. Theta is the parameter, and if it depends how many twirls of the helix you want to show. If you want to just show one twirl, you do from theta equals 0 to 2 pi. If you want to do multiple twirls, you do larger ranges of theta. This is the radius of, the r is the radius of your helix, and c has to do with how much does the helix expand out in the z direction. If c is equal to 0, then you'll just have a spiral. And if z is greater than 1, then you'll have, it'll expand outwards. All right, so that's the mathematical definition. Now, how do we do this how do we plot this out in Python? Just slightly different from what was done before. Before we did plt.figure, just to create the figure, as we did up here. All right, and then we did plt.plot. So the plt.plot command, it plots to whatever the current axis is. An axis is like an x, y, and z axis. You know, you can send your plot to a certain axis. Since we're doing a three-dimensional plot, we have to do it slightly differently. The first thing we do is create a figure, plt.figure, and this is a reference to that figure. Fig is a reference to the whole figure. And then we have to do a second step, figure.add_subplot, projection equals 3D. This is the way you tell Matplotlib that, hey, I want this axis to be a three-dimensional axis instead of the standard two-dimensional axis. And this function, add_subplot, returns a reference to the axis. So I have a variable that x that refers to that particular axis. This number here, 111, this means that we're just going to have a single axis in the figure. You've seen papers, I'm sure, where you have 8 different subfigures, 8 different axes in the figure. So you can modify this if you want to have a multi-part figure. All right. Questions so far? All right. The next thing we're doing here is we're doing theta is equal linspace from -4 pi to 4 pi, and we're doing 100 equally spaced points. All right. Notice what we have here, np.pi. So the NumPy library has a bunch of functions built in, and it also has a bunch of constants built into it. So let's do this. Let me. I'm just going to insert a cell above. All right, now I have a blank cell that I can run some stuff in. So if I just do print np.pi, what you'll see is 3.14. So NumPy has a lot of constants built in like that. All right, so this is going from -4 pi to 4 pi. We're creating a linear space, and this is our theta variable. R is a constant. We're saying the radius of our helix is going to be 2. And now we're going to calculate the x, y, and z values. This is the stuff that we actually use for the plotting. The x, y, and z values are all a function of the parameter theta, and it's also a function of r, and it's also a function of that parameter c, which we just have hard-coded here as 10. All right, so at this point, I'm just going to close these out right here, and I just want you to see print r, y, and z. So sorry, x, y, and z. So you can see, oops. Oh, I see. I'm going to comment these guys out too. All right, so these are your values of x. Here are your values of y, and then here are your values of z. So there's 100 different points for each one. I could set this equal to 10, but by having more points, the graph will actually look nicer. There won't be any gaps in it, or it won't look jagged. All right, so now we're just going to do the last thing here. We're going to do the plot. A couple commands here. So same command, plot, except notice that we do ax.plot instead of np.plot. np.plot means use the plotting function within the NumPy library. ax.plot is a different way that you can use Python and use functions within Python. This is called the object-oriented interface. Have any of you taken a course in object-oriented programming? 2 of you? Okay, that's fine. What object-oriented programming is that you have different objects or references to objects that you've created in your code, and if you, for example here, what do we do here? We ran this function called add_subplot, and it returned a reference to an axis. So that's a variable that represents one of the axes on the figure. So if I do ax.plot, what that's saying is do this plotting function within that particular axis. So as I said before, you could have multiple axes in a figure. You know, you could have a 2-part figure, a 3-part figure, and so on. This is saying to send the plot to this particular axis. And we're going to plot the x, y, and z variables, and the label. You don't have to have this if you don't want, but if you want to, it'll create a little label that says helix on it. This next statement says, create a legend on this particular axis. And the last statement is plt.show, which is just a general command to plot your function here. Okay, and this is what the function looks like. All right, we didn't label the x, y, and z axis. Yes, question?
How did you show your data again? What did you comment out?
Oh, sure. Yeah, 1 second here. So, you know, if I just want to print out like the values of variables, which is quite common, you know, you can just do print x, for example, and it'll print the. Yeah, you could also do print x and y and z, all 3 of them. You can even put like strings in here, and this is basically a list of things to print, separated by commas. All right, other questions? So far, so good? All right, so if you want to save one of these figures for, if I ask for the plot for an assignment, you can just download it here. Should be able to download it. I think my entire window is not showing. That's the reason why it's not working. You can also use screenshots. I think I showed, if you're using Windows, you can use that screen grabbing tool. What's the clipping tool? Snipping tool. There you go. Yeah, so you could just, if I ask for a screenshot, just click here like this, select an area, and save it as an image, and then you can upload it. As probably some of you have already done that for your assignments. All right. Okay, so this is how you do a 2-dimensional and 3-dimensional line in Python. Questions? Great. All right, so we did a 2D and 3D line. The next thing we're going to do is plotting a surface. The surface that we're going to plot is given by this function here. So we have a function z is equal to cosine of 2 pi r, where r is equal to the square root of x squared plus y squared. So we're plotting something in polar coordinates. If you remember, in polar coordinates, you have this radius r. We're going to be going over the coordinate system next, but this just so you know, this is a function z as a function of x and y. So we have x, y points on the bottom here. And then at every single point, x, y, we're going to calculate a value for z. And then we're going to plot that as a function, as a surface here. All right, and Python can make these nice figures here where you have the surface and it's colored based on what the value of z is. And you have a nice little color bar here that shows you that this is the highest value and this is the lowest value. Then we'll also do like something called a contour plot and a filled contour plot. So the first thing we're going to do is define the function and the grid. So let me just go right over to the notebook. All right, surface plots, here we go. So since we're done with this one, I'm just going to close down this window here. And when you close down the window, the notebook is also supposed to shut down. If it doesn't shut down, you can also click on this here. The green means it's currently on. I can click on this one and say shut this one down. And then I'm going to do the next one here. Surface plots. All right, let's just check in real quick. Falak, if you have any questions, feel free to ask them on the conference. All right, next one, 2D scalar functions. So this will go a little bit faster, I hope. So we have the same import statements as before, so we don't need to go over those. But let's remember that we have to execute that if we want to run the other ones. So just press Control Enter if you want to run that code and stay in the same cell, or press Shift Enter if you want to run that code and go to the next cell. All right, now this cell, you're going to see that first we're going to define the function, and then we're going to plot it. All right, so when you're plotting surfaces, let's remember one of the key things that you have to do here is you have to define a grid of x and y points. All right, just like we did before when we used linear space, lint space to create a vector of x points, we have to do a vector of x points, and then we have to do a vector of y points also. Now, I'm just going to copy this over to a different cell. There we go. Just so you can see what this particular code does. Now, I'm going to change n to 5 just for this particular example so you can see what's going on here. We're going to print xl and we're going to print yl. All right. So XL is, we said we're going to create a linear space between -1 and 1, 5 equally spaced points. So -1, 0.5, 0, 0.5, and 1. And you can see the same for YL. Now, these are vectors, right? If you want to plot a two-dimensional surface, you don't want to calculate z just along this axis or just along this axis. You want to calculate along this entire area spanned by x and y. So you want to calculate z for every single point in this two-dimensional space. So because of that, we have to use this function called meshGrid. What meshGrid is going to do, it's going to create a two-dimensional matrix of values. And I'll show you what that looks like. Different row. This is what your x vector looks like. 5 equally spaced points on the x-axis. Then you have 5 equally spaced points on the y-axis. But again, you have to create a two-dimensional vector, a two-dimensional area. And every single point in that area, every single point in a two-dimensional space has an x-coordinate and a y-coordinate, right? Every point in a three-dimensional space has an x, y, and z coordinate. So when we do this meshGrid function, we are creating all the points, all the possible values of x, and all the possible values for y in that two-dimensional space. So how this looks like is that the first point here, the first point is x equals -1, y equals -1. The next point in that two-dimensional space is x equals -0.5 and y equals -1. Then x equals 0, y equals -1. All right? So what meshGrid is doing is taking all the possible values of x and permutating them with all the possible values of y so that your x, so you have two different two-dimensional matrices. This defines all the x points, and this defines the x coordinates of all the points in the two-dimensional space. This defines all the y coordinates of the two-dimensional space. Questions? Does that make sense to everyone? So if you want to do a three-dimensional space, you have to use meshGrid with x, y, and z. All right. So I just showed you a small value of n so that most of the time we use quite a large value, like 50 or so. And then you're going to get a massive matrix like this. It's better for plotting if you have more numbers of points. All right, so now that I've done that, let me just delete this cell. Cell, delete, edit, delete. There we go. And we're just going to go back to this cell. So we know what this meshGrid portion does here. Now we're going to define our function z is equal to f of x, y. In order to define the function, you don't have to do it this way, but I first define the variable r. R is the square root of x squared plus y squared. And so you know how we created that variable x and variable y? They're both two-dimensional matrices. So at every point in that two-dimensional space, you're going to calculate a value for r. And so r is going to be a two-dimensional matrix that's the same size as x and y. And then for every point in R, you're going to calculate a value for z. So the function that we're plotting is a cosine of r times pi times 2. All right? Questions? All right. I'm just changing the size here so it's a little bit smaller so it's easier for you to see. And I'll go to full screen here so it's also a little bit easier as you can see. All right, so when I run this code, what's going to happen here, it's same as before. We create a figure, we add a three-dimensional axis to it, and the third command here is we are going to plot what's called plot surface. This is similar to that surf function in MATLAB, surf and surf C to plot a two-dimensional surface. What you have to give it the x and y values and the z values, and it'll plot a surface that way. And the color map that we're using is called cool warm, which basically creates a color map consisting of red to blue values. There are other color maps available, like a jet color map or grayscale color map, and so on. This returns a reference to that surface plot. Okay, we need that reference because when we want to make the color bar, you need to give it that reference there. All right, after this, we're just setting the x and y and z axis labels. You run this, and there you go. Those are your x, y, and z values. I made the plot a little bit smaller so it's easier to see, but as you can see, you can adjust the size of the figure up here. This is the width and this is the height. So let's make this a little bit wider. There we go. All right. Now, with three-dimensional graphs like this, you could actually click on it, and you should be able to rotate it. There we go. And look at it from different directions. Very nice for visualizing surfaces like this. All right, and you can actually save it in whatever orientation it was last. All right, questions? Yes, back there.
Does the compiler automatically match the z-axis to how many how do I put this, the intervals that are on the x and y axis? So you use intervals.
it auto scales. It auto scales the z-axis.
And so if I didn't define how many intervals I wanted for x and y, what I did for z, would it work the same way?
If you didn't define the intervals for x and y, okay.
Like if I just did -1 and 1, but we got rid of the n, but then I had a certain amount of intervals I wanted for my z-axis, would it still auto adjust?
You're saying here if you changed the n?
Just got rid of it.
Oh, just got rid of it.
Yeah. And
well,
then
it would give you an error because the lin space function creates an equally spaced set of points. If you leave out this, you have to indicate to it. You have to tell it how many points you want.
So it's not like a default.
I don't think so. I don't think there's a default in that one.
Oh.
Yeah. But just for kicks, like if you were to plot this with less points, let's just do it with 5 points instead of 50, then your plot is going to look like this. It's going to look very jagged.
Okay.
The more points you calculate, the finer it's going to be. So let's make this 100 now, and you'll see that you have a very nice smooth plot. Just like MATLAB, like you have to actually choose the number of points you want to plot. If you plot a ton of points, then it'll be computationally intensive, especially for three-dimensional functions. Good question. Did we have a question up here too? Is there another question? Okay. All right, good. All right, next part. Now what we want to do is we're going to create a contour plot. So that's the second thing we're going to do. So there's different ways of visualizing a surface like this, a surface that's a function of x and y. You can make the whole 3D thing, and I think that's great because it allows you to visualize it. But sometimes another way of visualizing the same thing is to use a contour plot. So the contour plot, you can think about this as a top-level view, looking at this function from the top. So, if I were to take this here and I just scooch this down here like this, and I'm looking at it from the top, this is what a contour plot might look like. There's two types of contour plot, a filled contour plot and a non-filled one. What we're looking at here is the filled contour plot. That's going to be the third one that we do. But this type of contour plot, a non-filled one, what it's doing is that it is plotting out lines that have equal elevation, equal z values. So the intuition here is that, again, if any of you have gone on hikes, have any of you used a topo map before? Okay, I see one of you have. Yeah, what's your name?
Joseph.
Joseph? Okay, so in your topo map, you notice how they have like lines that each one of those lines that show, that every point on that line is at the same elevation.
Right.
So if you have a mountain, for example, you'll have a series of concentric lines like you do here. Like let's look at this example. We know that we have this peak in the middle here, right? The middle of this function, we have a peak. And so you see a series of concentric circles, and that indicates to you that that you have this, you have a peak in the middle, and these lines indicate that they're going down from there. The definition of a contour plot is this, is that every line that you see in the contour plot has the same elevation. So if I were to walk around this circle like this, I would remain at the same elevation. If I walk around the red circle here, I would be I'd be at a different elevation, but different elevation than the blue line. But if I stay on this red circle, that means I'm staying at the same elevation. And basically, the way that a contour plot is made is that you have you figure out what is your range of z. In this case, z goes from negative 0.75 to 0.75. And you create, let's say 10 different contours, 10 different values between 0.75 and negative 0.75, and draw the lines at which those values occur. Right? If that doesn't make sense to you, think about it in terms of the topo map. Each one of these are equal values. At any particular line, the value of z along that line is the same along that line. All right? And the way you do the contour plot is actually quite simple. It's just a few commands. You don't need to actually. I take that back. It's not a few different commands. It's a few different commands here because we've already defined our x, y, and z. All right, we already did define the function here. We defined the mesh grid. So all we have to do here is just do this function plt.contour. This levels function says I want to pick 10 different contours, 10 equally spaced values between the highest and lowest values of z, and you can see them appear on the contour map here. If I change this, let's say I make this 5 instead, you will see that there's fewer lines there. And if I say 50, you'll also be able to see that the lines start to bleed together. All right, so just use 10 here. All right, and so any questions on the contour plot? Okay. MATLAB has very similar functions. In fact, I think they have the same name. The last plot is a filled contour plot, and this is where let me just do this so you can see the difference. This is what a contour plot looks like. It just has the lines, and the filled contour plot actually fills in the space in between the lines with the color representing the z elevation. So this is pretty much a top view of the three-dimensional map like this. All right, what is this map showing? The red areas are showing the highest elevation, the blue areas are showing the lowest elevation, and so forth. And the gradient of color shows you the different elevations on the map. So this is a two-dimensional plot that essentially does the same thing. You don't need to make a 3D plot and then convert it into 2D and rotate it and stuff. This will just give you the top view very nicely. And you can choose the number of levels you want. I like to use a lot of levels here so that it creates a nice, beautiful plot like this where you can see the color gradients and stuff like that. So again, what this is telling you, the highest elevation is in the middle because it's red. The color gradients are showing you where the lower elevations are. So there's a lower elevation here, and then another high elevation here at the top. All right. Okay. Last thing we're going to do, because, in this example with MATLAB, what we did is we plotted a surface, and then we also plotted the gradient field underneath it. So that's what we're doing here on the last part. So what I'm doing is I'm actually plotting this contour, a filled contour map, and then I'm superimposing the gradient vectors on top of that. You see how these are like two overlapping plots? So you can do that in IPython, just like you can do it in MATLAB with a hold function. So first thing I'm doing here is I'm calculating the gradient. And NumPy has a very simple function that you can use to calculate the gradient. All right, what do you have to supply this function? You have to tell it what your z values are, and then you also have to tell it the spacing between the x and y vectors. All right, that's a little detail that you have to know in order to use this function. But that brings me to an important point. How do I know what to use these functions? You're obviously not just going to be able to copy and paste all the code that I'm showing you. The nice thing about Python is that the documentation is extensively available online. So if you just type in NumPy gradient, or better yet, let's say you don't even know how to calculate the gradient. You could do Google searches like gradient in Python. And I can almost guarantee you, because it's an open source type thing and like so many people around the world are using it, you'll either find some kind of suggestion on a website like Stack Overflow, or you'll find a link to the actual function. All right, so happens that this actually gives us a link to the website that documents the entire NumPy system. So you'll see here that there's an organization called SciPy, which is short for Scientific Python, large organization that maintains these libraries. You can see all the documentation that they have. There we go. So they have a NumPy developer guide for people who actually want to contribute to the code, and then they have all these reference guides. They maintain the NumPy library, and they also maintain something called SciPy, which is a scientific Python. There's a separate library for machine learning as well. But yeah, the reference guide you can find here, user guide you can find here. So if we click on this NumPy manual and you click on the reference, you'll see all the functions that are available to you in NumPy. And you can also search for it here. So I would actually browse this if you're interested in getting familiar with it. You can just read through all the functions that are available. The function that we were looking for was gradient. So we can just do a quick search on that, gradient. It'll take us to the numpy.gradient function. And you can see here all the different parameters that's required for the gradient and what it returns. So this is a list of parameters. So you have to supply it in an n-dimensional array containing the samples of a scalar function, so the z values. And you also have to tell it the spacing between the values. Okay, meaning the spacing between the x and y points. Every point in your two-dimensional space, how much space is between them. And then this will return to you a set of n-dimensional arrays corresponding to the gradient. So let's look back at the function here. Look back at the example here. So gx means the gradient in the x direction, and then the gradient in the y direction is equal to this function. And the spacing between x and y points is 2 over n here. And now what we're going to do is we plot the figure. The first thing we do is we plot the filled contour map, just the same as what we did before. We make a color bar. And then on top of that, we do this vector plot using a function called quiver, and I'll get into that in the next in the next part here. All right, so this scale controls how big the arrows are. So the quiver function, it plots a vector field. You have a series of x coordinates, a y coordinate. the gradient in the x direction and the gradient in the y direction. That's the vector that we want to plot. And this is how big the arrows are, and there you go. So this is plotting the gradient. And when you look at this, you can get an intuition of the gradient, same as the MATLAB plot did. This blue ring here, do you guys remember, was that a hill or a valley? It was a valley, right? So in the valley, at the bottom of the valley, what's the slope? It's 0. It's flat at the bottom, right? So wherever you have flat, wherever the function is flat, there's no gradient. The gradient's equal to 0. That's why you see that the gradient vectors are basically become 0 in the middle here. But if you are on the slope, you know, the top, I should also say that the top of the peak, that where the peaks are, the gradient is also 0, because when you're on top of the mountain, you're also, like, your slope is 0, right? But when you're on the side of the mountain, then there's a gradient here. And the gradient vectors, you can see that they're pointing upwards. I think we may have a mistake here, actually. I think I have an error here, because the gradient vector should point in the uphill direction. You can see that it's pointed in the uphill direction here, but you can see that it's pointed in the downhill direction here, right? So there must be some kind of coding mistake that I made here. So rather than try to figure out what that is, I'll just say that this is, you should always check over the work that you do, and you know, when I figure that out, I'll just send you all an update of it. Bonus points to anyone who can figure out what I did wrong there. I'm looking up the gradient function. Questions? Awesome. All right. So now we plotted surfaces. Now we're going to do plotting vector fields. Again, this is you're going to be defining a linear space. We'll do the two-dimensional field first. Same import statements as before. Let's go right to the notebook. We're going to plot a two-dimensional vector field and a three-dimensional vector field. Okay. Let's close this notebook down. Yeah, just leave it. Vector fields, here we go. All right. So import statements are the same as before. We're going to import the NumPy library, the Matplotlib, 3D stuff. All right, so for the 2D vector plot, we first create a linear space of x and y points. We're going from -1 to 1, 10 equally spaced points, and then we create a mesh grid for x and y. All right, now here's the difference. Here's the difference between surfaces and vectors. So the vector has an x direction and a y. It has an x component and a y component, right? So you have to define what the x and y components are for every single vector on the map. All right, so let me give you like just to see if everyone's with me here. What is the size of XL going to be? What's going to be the size of that array? First of all, is it going to be a one-dimensional array or a two-dimensional array? Based on this code here.
One-dimensional.
It's going to be one-dimensional, that's right. And one way, I'm just going to show you another hint here. So if I copy this code up here. So there's a function called shape. So if I want to print the shape of this thing, I just do this. All right, what's the error? Okay, I didn't import my libraries yet. You can see that. So let's import this first and then run this. All right, so what this is telling us is the shape of the XL. XL is just a vector, so it's the size of it is in 10 in this direction, and it doesn't have any other second or third dimension. All right, what's the shape of YL going to be? All right, it's going to be the same. What is going to be the shape of the mesh grid? Two-dimensional, right. So let's copy this up here so you can see here. and let's do the shape of x. You see how x is now 10 by 10? It's a 10 by 10. It's a two-dimensional array. And then the same thing for y. If we did the same thing for y, we'd see that. All right, so we talked about mesh grid already, so I won't belabor that. Now, for every point in that two-dimensional space, let's go back to this plot here. What we want to do is every single point on this two-dimensional space, we want to find what the vector is for that. A vector has an x component and a y component. And the particular vector field that we're going to be plotting in this case is the same one that we actually plotted in the MATLAB. So let me just jump back to that. So we're plotting the vector field negative y times x hat plus x times y hat. And this vector field is kind of like a vortex vector field. It's a vector field that rotates in the counterclockwise direction. And so we have to define the x component, and we have to define the y component. And the way that we do that here is that we say u, this is just a convention. You can call the variable whatever you want, but I like to call it u. This is the x component of the vector. So u is equal to negative y. And then the v component, which is the y component, is equal to x. Right? We're literally just taking the equation here. All right, we've defined values of x and y in this previous statement here, and now we're defining the vector field u and v. All right, in order to create the vector field, we first create the figure. Then we use this quiver function. Quiver function, basically what it does, it draws a bunch of arrows. This is where the x coordinate of the vector, this is the y coordinate of the vector, and this is the x component of the vector, and this is the y component of the vector. So keep in mind there's the difference here. The x and y coordinates tell you where that arrow is going to start. And then the u and v values tell you where how large that vector is and what the direction of that vector is going to be. All right, so after you execute this code, you get something like this. Everyone with me so far? All right, so we go on to the three-dimensional one. Has everyone been able to just run the code? Have you had any errors or anything? All right, good. Yeah, you should be able to run this on a Windows system, a Linux system, whatever. You know, Python's pretty cross-platform. All right. For the three-dimensional vector plot, very similar to what we did before, you're going to define a mesh grid that consists of x, y, and z coordinates. And we're just using, to make sure that our vector field doesn't get out of control, that we're not plotting too many vectors, and it becomes really hard to see. We're just doing 5 in the x and y and z direction. So how many vectors am I going to get if n equals 5? So we have 5 equally spaced points in the x direction, 5 equally spaced points in the y direction, 5 equally spaced points in the z direction.
125.
What's that?
125.
We're going to be drawing 125 vectors. That's right. 5 times 5 times 5. All right, and if you took the shape of any of these matrices, x, y, and z matrices, you'll see that they are 5 by 5 by 5. All right, here we define the vector field in the x hat, y hat, and z hat directions. So we're just, I'm just picking like a very simple vector field. This is a vector field that diverges from the center. This is the equations for that. The next plot is we create the 3D plot. We use the quiver function, and notice the difference here. Here we did a quiver function with x, y, u, and v. And we just called that from the PLT interface, meaning like that's the Matplotlib PyPlot interface. When we do the same thing in a three-dimensional setting, we have to do that slightly different command where we first create the figure, and then in that figure we create a subplot, and we get an axis, and on that particular axis we do this quiver plot. That's the first difference. The second difference is that notice we have x, y, and z here rather than x and y. And then we have u, v, and w. So this is the x component of the vector, the y component of the vector, and the z component of the vector. And you could set the length here as well, just to make it a little bit easier to visualize. X, y, and z labels, and then you show this, and you get something like this. All right, you can rotate this in different directions. You should be able to. Okay. Sometimes you need to run the import statement, this directive, a second time in order to get the notebook interface, which allows you to rotate the plots. So I'm just running that code again here, and you can now see that now I can rotate this vector field. All right. So what you can see here, just from like this is a vector field that I chose that has the x component is equal to the x value, and so on. So the vectors get larger the farther you get away from the origin. All right, and there's 125 vectors here. You can see how it can get pretty crazy if you increase the n from 5 to something else. Like let's, if we did like 20 here, you'll see that you're going to get a really insane number of vectors that you can't even see it anymore. All right. Great. That's it for the vector fields. Let's go on, and actually I neglected to show this one. I probably should have shown this one first, but if you want to plot a single vector or just a couple vectors, which you'll have some things in your homework for doing that, you can use the same import statements as here. And I'll show you some quick ways to just plot a single vector. This is just a simpler version of what we did on the previous one. So we're going to define a vector, and this vector is 0 to 5, originating from the origin. All right, so we're basically going to tell Matplotlib to draw an arrow. It's going to start from the point 0, 0, 0, and the length of the x, y, and z components is 0, 2, and 5. So we tell IPython x, this is the starting coordinate. This is where we start the arrow, the head of the arrow, and these are the x, y, and z lengths of the arrow. Here we create a three-dimensional plot, same as before. We use the quiver function for a three-dimensional arrow plot. And then here, this is something you haven't seen yet, but you could set the limits if you choose. This was getting to your question about like, how does IPython know like what to set the z equal to? You can actually manually set them if you wish. And for some of the functions, the auto-scaling works really well. For this particular one, the auto-scaling didn't work very well, so I manually set the values here. So I'll just go ahead and show this. And you can see that you have the vector here, and you can twist and turn it in these different directions. All right, so this is just drawing a single arrow. I'll show you what happens. We can change the limits. We can make this from -5 to 5 in all the different directions. Draw it again, and then the arrow will, of course, appear larger. That's a single vector. Ignore these, ignore these warnings here. Now, let's say you want to plot 3 vectors at the same time. So in this example, we have 3 vectors. They're all originating from the origin, and we're going to plot them. So this is a kind of a demonstration of like adding vectors together. So this is vector A, this is vector B, and this is the vector C, the sum of A and B. So all 3 of the vectors are originating from the origin. So when we created a single vector, here's what we did. We just created, here's the x, this is where the x, y, and z values are where the vector is originating, and here's the length of the 3 vectors. So now what we're going to do is we're going to create a list of 3 vectors. All right, so there's going to be 3 x coordinates, 3 y coordinates, 3 z coordinates, and then 3 x components, y components, and z components. So what I want you to notice here is that the first column the first column or the first entry in x, y, and z, these are the x, y, and z components. This is all relates to the first vector. All right, this is all for the first vector. And then these u, v, and w values, this is all for the first vector. You notice that the first vector that we're plotting here is 0, 2, 3. So you see 0, 2, 3 appear in the first entries for u, v, and w. The second vector appears here, 3, 1, negative 2. Third vector is 3, 3, negative 1 here. All right, so in order to plot three vectors, we need x, y, z coordinates for all three. We need u, v, w components for all three of them. And then we use the same commands as we did before, as the previous one, to plot all three at the same time. And then you're going to get your three vectors. You get your three vectors like this. All right. So really, the reason I said I should have gone over this one first is because this just shows you how to plot basic arrows. That's what the quiver function does. In this case, we plotted just a single arrow. In the second example, we plotted 3 arrows. And here what you're doing is you're just plotting a whole bunch of arrows. You're plotting a massive list of arrows in a 2D and 3D field. Questions? Excellent. All right, we already went over this. Calculating the gradient in Python, you have the gradient function. And like I said, we noticed that there seems to be some kind of error. I'll get back to you on that. There should be, the gradient should be pointing in the direction of maximum slope. All right. I want to get into coordinate systems today. We have 5 minutes. I guess we can get a quick start on it, but we probably won't finish it. Today. So before we get into that, any last questions on the Python stuff? Okay. Also, before I forget, there is a homework assignment that's posted today. It's going to be due next Wednesday. It's going to be longer than the previous one, right? Because this is, all this vector math stuff, it takes time, it takes effort. So my suggestion to you is that you get started on the homework sooner than later. Get started on the questions. You should be able to answer. Actually, for this homework, you should be able to answer all the questions because we covered gradient.
So the homework is 10 questions?
That's right. It's posted on Canvas. There was a change to it that was made last night. So please make sure you have the most recent version. And I was planning on bringing your graded homework assignments back, but I will bring those back to you on Monday. You should be able to see the grades for those before Monday. You'll be able to see them. I'll post them on Canvas. All right. So let's last 5 minutes. Let's talk about these 3 different coordinate systems. There's 3 major coordinate systems: the Cartesian, cylindrical, and spherical. They are all used for visualizing 3-dimensional problems. How many of you have worked? Well, all of you have done the Cartesian system before. How many of you have worked with the cylindrical system before? Okay, a couple of you. And how about the spherical coordinate system? Again, a couple of you. So I imagine it was just multivariable calculus, right, where you did some of that stuff. Okay, so yeah, just to warn you, electromagnetics is a lot of multivariable calculus. So it is to your advantage to make sure that we learn these or review them if you've already seen them. Depending on the type of problem we are working on, you're going to choose an appropriate coordinate system. So if I go over some of these really quick, I just want for you to get an intuition of them. The Cartesian coordinate system, you already know. It has x, y, and z coordinates, and the unit vectors are in the x hat, y hat, and z hat direction. So these are, this is a orthogonal coordinate system where the vectors are basically linear. The cylindrical coordinate system is where you define things in terms of 3 coordinates: r, theta, r, phi, and z. So r is how far away you are from the z-axis, so it's like your radius. It's kind of like a polar coordinate system. How many of you have worked with polar coordinate systems before? All right, it's kind of like a polar coordinate system where the r is the distance from the z-axis. Phi is the angle going from the x-axis, so it's this phi angle here. And then the z is just very similar to the Cartesian coordinate system. It's just the z-axis. All right, so I'm just going to pose this to you. Like this is the spherical coordinate system. In the spherical coordinate system, you don't have x, y, or z. You have r, theta, and phi. So r is the distance from the origin, right? How far are you away from the origin? Theta is the zenith angle, so this is the angle measured from the z-axis, and then phi is the angle measured from the x-axis. All right, so there's two angular coordinates in the spherical system. Whether you're in Cartesian, cylindrical, or spherical, there are three different coordinate systems that allow you to locate a point. So this point M can be located by x, y, and z coordinates. It could also be located by r, phi, and z coordinates if you're in the cylindrical coordinate system. It can also be located by r, theta, and phi coordinates in the spherical system. Right? You can, in principle, you can do any problem in any one of the coordinate systems that you choose. We often use the Cartesian system for a lot of the problems because it's relatively easy to use. There's less trigonometry that you have to do with them. But we're going to find out in this class that there are certain situations where you would prefer a certain coordinate system over others. So if you have geometries that are very box-like, you want to use a Cartesian coordinate system. What if you have if you have something spherical, then you want to use the spherical coordinate system. For example, you guys remember this example of the electric field or the gravitational field from a planet, right? What type of symmetry is that going to have? Would that be best to use Cartesian, spherical, or cylindrical? Spherical, right, because it has spherical symmetry, right? The object is a sphere, the gravitational field has spherical symmetry. What about a wire? Let's say we talked about the Biot-Savart law where we have current going through a wire. The cylindrical coordinate system. Why would we use the cylindrical coordinate system there? Yeah, exactly. The wire. You think about the wire as a cylinder. You can think about, does the field or geometry that we have, does it have Cartesian symmetry? Is it box-like? Does it have cylindrical symmetry? Is it a cylinder-like? A wire is basically a cylinder, as you point out. Or does it have spherical symmetry? Does the object look like a sphere? Based on those three simple questions, you can decide what coordinate system you should use for that particular problem. And so next time in class, we're going to go over the different coordinate systems, and then we'll also get into the differential volumes and the equations that you're going to use to do coordinate transformations and vector operations in the different coordinate systems. All right, thanks for your attention. Have a good weekend. Please get started on the homeworks. If you have any questions on them, please feel free to email me.
Is there more than 3 coordinate systems?
Is there more than 3? Yeah. There's other coordinate systems too. Like mathematicians and astrophysicists, they use like 4D, 5D.
Oh, okay, just higher
systems. Yeah.
Okay.
But these are the most popular ones used in 3-dimensional space.
I have a question about exam. Do we have to memorize the formula, or you gonna give a formula for us?
Do you need to memorize the formulas? No, I will give you. I'll give you formulas on the exam, and you'll also be allowed to bring 1 page of notes front and back for writing your own formulas.
Can you post the formula before the exam, like 1 week or 2 weeks or something?
Yeah, I will do that. Mhm.